The single-minded case. This section focuses on the twin goals of computational complexity and strategic behavior, while leaving out completely the third issue of the representational complexity of the valuation functions. For this, we restricted ourselves to players with very simple valuation functions, which we call single-minded bidders. Such bidders are interested only in a single specific bundle of items, and get a specified scalar value if they get this whole bundle, or any superset and get zero value for any other bundle. Definition 11.3. A valuation V is called single-minded if there exists a bundle of items S star and the value of V star in R plus such that V of S equals to V star for all S which is a subset equals to S star, and V of S is equals to 0 for all other S. A single-minded bid is the pair S star V star. Single-minded valuations are thus very simply represented. The rest of this section assumes as a common knowledge that all bidders are single-minded. Computational complexity of allocation. Let us first consider just the algorithmic allocation problem among single-minded bidders. Recall that in general, an allocation gives disjoint sets of items Si to each bidder I and aims to maximize the social welfare, the summations of Vi of Si, summing for all index I. In the case of a single-minded bidders, whose bids are given by Si star, Vi star, it is clear that an optimal allocation can allocate to every bidder either exactly the bundle he desires, Si equals to Si star, or nothing at all, Si equals to empty set. The algorithmic allocation problem among such bidders is thus given by the following definition. Definition 11.4. The allocation problem among single-minded bidders is the following. Input: Si star, Vi star for each bidder I equals to 1 to 3 until n. Output: a subset of winning bids, W, which is a subset equals to the set 1 to 3 until n, such that for every I not equals to j in W, Si star intersect Sj star equals to the empty set, i.e. the winners are compatible with each other, with maximum social welfare, the summations of Vi star summing for all I in W. This problem is a weighted packing problem and is incomplete, which we will show by reduction from the independent set problem. Proposition 11.5. The allocation problem among single-minded bidders is NP-hard. More precisely, the decision problem of whether the optimal allocation has social welfare of at least k, where k is an additional part of the input, is NP-complete. Proof: we will make a reduction from the NP-complete independent set problem. Given an undirected graph G equals to V and a number k, does G have an independent set of size k? An independent set is a subset of the vertices that have no edge between any two of them. Given such an independent set instance, we will build an allocation problem from it as follows. The set of items will be E, the set of edges in the graph. We will have a player for each vertex in the graph. For vertex I in V, we will have the desired bundle of I be the set of adjacent edges Si star equals to the set of little e in capital E such that little I in little e, and the value be Vi star equals to 1. Now notice that a set W of winners in the allocation problem satisfies Si star intersect Sj star equals to empty set for every I not equals to j in W, if and only if the set of vertices corresponding to W is an independent set in the original graph G, the social welfare obtained by W is exactly the size of this set, i.e. the size of the independent set, it follows that an independent set of size at least k exists, if and only if the social welfare of the optimal allocation is at least k. This concludes the NP-hardness proof, the fact that the problem of whether the optimal allocation has social welfare at least k is in NP is trivial, as the optimal allocation can be guessed, and then the social welfare can be calculated routinely. As usual, when a computational problem is shown to be NP-complete, there are three approaches for the next step: approximation, special cases, and heuristics. We will discuss each in turn. First, we may attempt finding an allocation that is approximately optimal. Formally, we say that an allocation S1, S2, S3 until Sn is a C approximation of the optimal one if for every other allocation T1, T2, T3 until Tn. And specifically, for the socially optimal one, we have that the summations of Vi of Ti summing for all I over the summations of Vi of Si summing for all I is less than or equals to C. Perhaps a computationally efficient algorithm will always be able to find an approximately optimal allocation. Unfortunately, the NP completeness reduction above also shows that this will not be possible. Not only is it known that the finding the maximum independent set is NP-complete, but it is known that approximating it to within a factor of n to the 1 minus epsilon for any fixed epsilon greater than 0 is NP-complete. Since in our reduction, the social welfare was exactly equal to the independent set size, we get the same hardness here. Often this is stated as a function of the number of items n rather than the number of players n. Since m, which is less than or equals to n squared, m is the number of edges, n is the number of vertices, we get proposition 11.6. Approximating the optimal allocation among single-minded bidders to within a factor better than m to the 1 over 2 minus epsilon is NP-hard. As we will see in the next subsection, this level of approximation can be reached in polynomial time, even in an incentive-compatible way, which is the topic of the next subsection. Second, we can focus on special cases that can be solved efficiently. Several such cases are known. The first one is when each bidder desires a bundle of at most 2 items, the size of Si store which is less than or equals to 2. This case is seen to be an instance of the weighted matching problem, in general known by bipartite graphs, which is known to be efficiently solvable. The second case is the linear order case. Assume that the items are arranged in a linear order and each desired bundle is for a continuous segment of items, i.e. each Si star is equals to j to the I plus 1, and so on until k to the I. For 1 less than equals to j to the I less than equals to k to the I less than equals to m. Think of the items as lots along the seashore, and assume that each bidder wants a connected strip of seashore. It turns out that this case can be solved efficiently using dynamic programming, which we leave as an exercise to the reader. Third, an NP-completeness result only says that one cannot write an algorithm that is guaranteed to run in polynomial time and obtain optimal outputs on all input instances. It may be possible to have algorithms that run reasonably fast and produce optimal or near optimal results on most natural input instances. Indeed, it seems to be the case here. The allocation problem can be stated as an integer programming problem and then the large number of known heuristics for solving integer programs can be applied. In particular, many of these heuristics rely on the linear programming relaxation of the problem, which we will study in section 11.3. In a general setting, it is probably safe to say that most allocation problems with up to hundreds of items can be practically solved optimally, and that even problems with thousands of or tens of thousands of items can be approximately solved quite well.